Hello everyone, very good evening. Welcome back to the YouTube series of Discrete Mathematics in which we are discussing set theory and algebra. Okay, so let's start the session. Please tell me audio video is clear? Okay, thank you. Everything is clear. So, very good evening once again. So let's begin the session. So what we have discussed in the last class is that in the last class we have understood the concept of least upper bound in our post-it. Please make sure that 2-3 days has passed so you remember all the concepts which we have discussed in the last class. So least upper bound. So what do we mean by least upper bound? So for two elements A and B, we are looking for a upper bound such that it is at the upper side of A as well as on the upper side of B, but there is no other upper bound apart from, let's say, if we say that there is an element C which is at the upper side of A and the same element C is at the upper side of B, then C will be the upper bound of A and B. If there is no element D which is on the lower side of C, then ultimately C is the upper bound. C is the upper bound of A and B, and there is no other upper bound of A and B. There is no other upper bound of A and B which is at the lower side of C. Therefore, C will become least upper bound. That we have already discussed, just a quick revision. Similarly, greatest lower bound. So just like upper bound, we will look at the lower bound. That there must be an element which is at the lower side of A as well as on the lower side of B, and that should be the greatest one. So it will become greatest lower bound. Apart from that, in the last class, we introduced the concept of Hasse diagram, which is also known as a posset diagram. Why do we call it a posset diagram? Because it is created for a posset. Posset diagram or Hasse diagram is generally constructed for a posset. What are we going to discuss in the today's session, sir? We are going to understand, or we are going to introduce the concept of lattice, that what actually a lattice is. So please don't think that it will be a new thing. Lattice is nothing but a special type of posset. So don't worry, don't think that we are going to learn a new concept. No, it's not a new concept. If your posset follows or represent certain properties, then that particular posset will be called a lattice. Apart from that, we'll understand different types of lattice, and those different types are basically on the properties represented by your lattice. So posset will represent certain properties and it will become a lattice, and if some other properties are also followed in a lattice, then it will represent different types of lattice. Anyway, not a big deal. So let's understand. Let's have a quick revision of our posset diagram. So what did we say? So in our posset diagram, the posset, if I say A with respect to relation R is a posset, then for every element of set A, there will be a vertex in the Hasse diagram or posset diagram. So there is a vertex corresponding to every element of the set. Now, elements of this set A will relate with respect to this relation R. So when exactly there will be an edge in the Hasse diagram, sir, an edge will be present in the Hasse diagram if your element A relates with B and there is no element X such that A relates with X and X relates with B. Sir, why? Why? That if A relates to B, then there should not be any element X such that A relates to X and X relates to B. Because in a Hasse diagram, we do not represent the transitivity. Transitivity is already implied. Transitivity is already implied by the Hasse diagram, because we know that we are constructing it for a posset and the partial order relation will be reflexive, antisymmetric and transitive. So we know it will eventually be transitive. Therefore, we do not represent transitivity explicitly. So there will be an edge between A and B if A relates with B, but there is no element X such that A relates to X and X relates to B. Okay, so that's one thing. Apart from that, sir, because relation R is a reflexive, therefore every element A will relate with A. So do we create an edge with respect to this relationship? No, we do not create an edge with respect to reflexivity. Otherwise, there will be a self loop at every vertex. So we avoid the self loop in the Hasse diagram and we simply say that okay, we don't need to represent it explicitly because we know that it is a Hasse diagram. It is created for a posset, so we know it will be reflexive. Therefore, transitivity is not represented, it is implied in the Hasse diagram. Similarly, no self loop, reflexivity is implied in the Hasse diagram, it is not represented. Apart from that, your Hasse diagram will be so that's the general statement. Generally, your hash diagram will be undirected, but some people may create the hash diagram using the directed edges. There is no problem with that as well. But anyway, if you are using a hash diagram in which there is no direction for the edge is defined, then in that particular case we will use upward inclination. What does it mean? If A relates with B, we know that A relates with B does not relate with A, because if A relates with B and B relates with A, then it will become symmetric pair and it is not allowed in the POSIT. So if A relates to B, then in the hash diagram A will appear at the lower side and B will appear at the upper side. So either this is that A relates with B, or you can draw an explicit direction in the edge and you can say that A relates with B. So that's the simple concept. We have already seen this. We have seen the hash diagram for different POSITs. So we have created the hash diagrams for all these POSITs. I'll just give you a quick view of all those POSIT diagrams. We are going to see them again while discussing the concept of lattice. So we'll visit all these hash diagrams once again before we start discussing the internal details of the lattice. So now the next definition. So this is the today's topic. We are going to introduce the concept of lattice. But before we jump to the concept of lattice, we first need to understand two special type of sublattices which are known as joint semi-lattice and meet semi-lattice. So these are two semi-lattices, not sublattice, semi-lattice. We need to discuss two different types of semi-lattice. So when exactly do we say that our POSIT is a joint semi-lattice? Do you remember that when I was defining the concept of least upper bound, I also called it as joint. Why? Because this least upper bound will be with respect to joint semi-lattice. So what does it say? Sir, in our POSIT, if least upper bound exists for every pair of element, it will be called a joint semi-lattice. What did we say? Sir, in a normal POSIT, it is not necessary for every pair of elements to have a least upper bound or greatest lower bound in the POSIT itself. It's not necessary. So if I give you an example, let's look at this. If I say 2, 3, 6, if I say 2, 3, 2, 3, 4. If I say 2, 3, 4, 6, if I create a POSIT diagram for this, then this will be 2, this will be 3, this will be 4, 3, 6, 2 divides 4, 2 divides 6. So this is your POSIT. So 2, 3, 4, 6 with respect to, let's say, with respect to divide. So in this particular POSIT, there is no upper bound of 4 and 6. There is no least upper bound of 4 and 6. Right? So in a POSIT, it is not necessary that the least upper bound will exist for every pair of element of the POSIT. But for a POSIT to become a joint semi-lattice, least upper bound should exist for every pair of elements. So that's the very first definition with respect to lattice, that is joint semi-lattice. What? Sir, a POSIT in which least upper bound exists for every pair of element. A POSIT in which least upper bound exists for every pair of element is called a joint semi-lattice. I'll give you a intuition for that, but it's okay. Let's go to this particular POSIT. So we have already created the POSIT diagram for 2, 3, 6, 12. Now, if you look at this, take any two elements from this set. Take any two elements from this set and check whether the least upper bound of that pair of element exists within the same set or not. So you'll eventually realize, let's say, sir, what is the least upper bound of 2 and 3? Sir, the least upper bound of 2 and 3 will be 6. Least upper bound of 2 and 6 will be 6. Least upper bound of 2 and 12 will be 12. 3 and 6 will be 6. 3 and 12 will be 12. 6 and 12 will be 12. 12 and 12 will be 12. So least upper bound exists for every pair of element. Okay. So in this particular POSIT, least upper bound exists for every pair of elements. So can I say that this is a joint semi-lattice? Okay. Anyway, so it is a joint semi-lattice. Yes, sir. Now, let's look at another diagram. Now, do we have the least upper bound of 4 and 6? No, sir. The least upper bound of 4 and 6 does not exist. So, if there exists any pair of element, in the POSIT for which the least upper bound does not exist in the POSIT, then that particular POSIT will not be a joint semi-lattice. So, can I say now? Go back to the same concept. Least upper bound of 6 and 9 does not exist. Therefore, It is not a joint semi-lattice. Come on, I'm just saying not a joint semi-lattice. I don't know whether it is a meet semi-lattice or not. It's not a joint semi-lattice, because in a joint semi-lattice, least upper bound should exist for every pair of elements. So if there is any pair for which the least upper bound does not exist, it will not be a joint semi-lattice. Next one is the meet semi-lattice. Now recall, when we discussed the concept of greatest lower bound, we also called the greatest lower bound as meet or infimum. Meet or infimum. So this meet semi-lattice is with respect to greatest lower bound. When exactly do we say that a poset is a meet semi-lattice? In a poset, if greatest lower bound exists for every pair of element. In a poset, if greatest lower bound exists for every pair of element, then it will be called a meet semi-lattice. Okay, sir. So a poset in which greatest lower bound exists for every pair of element is called a meet semi-lattice. Okay, simple concept. Let's go back to the same definition. Now, here, least upper bound exists for every pair of elements. So, can I say LUB exists for every pair of element? Therefore, it is a joint semi-lattice. Clear? Okay, sir. These are joint semi-lattice. But my question is, do we have greatest lower bound? Do we have greatest lower bound for 2 and 3? No, sir. Come on. Do we have greatest lower bound for 2 and 3? No, sir. The greatest lower bound for 2 and 3 does not exist. Greatest lower bound. Where do they meet each other at the lower side? They do not meet anywhere at the lower side. Therefore, greatest lower bound of 2 and 3 does not exist. So, if there is any pair of element, for which the greatest lower bound does not exist, then it cannot be a meet semi-lattice. So it is a joint semi-lattice because LUB, least upper bound, exists for every pair of element, but there are some pairs for which greatest lower bound does not exist, therefore not a meet semi-lattice. Not a semi-lattice. Let's go back to the next example. So here we have some pair of element for which least upper bound does not exist, therefore it is not a joint semi-lattice. But check, do we have greatest lower bound for every pair of element within this poset itself? Yes, sir. Take any two element from this poset, and if you try to obtain the greatest lower bound for that pair of element, then that greatest lower bound will be present in the poset. Clear? So greatest lower bound exists for every pair of element. I'll give you a simple trick to check that. This for every pair of element. Therefore, is a meet semi-lattice. So previous one is a joint semi-lattice but not a meet semi-lattice. This particular poset is a meet semi-lattice but not a joint semi-lattice. Now simple concept is, if there exists two or more maximals, it cannot be joint semi-lattice. If there exists two or more minimals, it cannot be meet semi-lattice. Clear? Simple concept is, if there exists two or more maximals, it cannot be joint semi-lattice because for those maximals the least upper bound will not exist. And if there exists two or more minimals, it cannot be meet semi-lattice. Now we have seen the definition of joint semi-lattice and meet semi-lattice. Now we'll talk about lattice. Sir, what is a lattice? So simple concept, a lattice is a poset which is a joint semi-lattice as well as a meet semi-lattice. That is a poset in which least upper bound as well as greatest lower bound exist for every pair of element will be called a lattice. So what, sir? A poset in which both both least upper bound as well as greatest lower bound. Least upper bound as well as greatest lower bound exists for every pair of element. Exists for every pair of element. Then it is called lattice. Clear? Okay, so what does it mean? If least upper bound exists for every pair of element, it will be joint semi-lattice. If greatest lower bound exists for every pair of element, it will be meet semi-lattice. So a lattice is nothing but a poset which is a joint semi-lattice as well as a meet semi-lattice. Okay, so let's go back and see. Sir, is it a lattice? No, sir. It is just a joint semi-lattice but not a meet semi-lattice. So when I say not a meet semi-lattice, therefore not a lattice. Therefore not a lattice. Okay, let's go to the next one. Sir, it is not a joint semi-lattice, therefore not a lattice. Come on. Next. Sir, what about this post? Let's look at this. Sir, two maximals, therefore it cannot be joint semi-lattice. Two minimals, therefore it cannot be a meet semi-lattice. So what can I say? Sir, neither a joint semi-lattice, so two or more maximals, therefore the least upper bound will not exist. Two or more minimals, so the greatest lower bound will not exist. So neither a joint semi-lattice nor a meet semi-lattice. Yeah. So if there are two or more maximals, it cannot be a joint semi-lattice. Two or more minimals, it cannot be a meet semi-lattice. So this is the opposite, but neither a joint semi-lattice nor a meet semi-lattice. Now let's go back to the other examples which we took. Sir, if you take this particular poset, then the least upper bound as well as greatest lower bound exists for every pair of element. Take any two elements. Take any two elements. Sir, this is the set of all divisors of 12. So if you take any two elements, their upper bound will exist. If no other upper bound exists, then at least 12 will be the upper bound. Similarly, it is the set of all divisors or all divisors. Therefore, one will also be present. So lower bound will exist for every pair of element. If no other lower bound exists, then one will be present, which will divide both the elements of the poset. Therefore, we can actually say that in this particular poset, least upper bound as well as greatest lower bound exists for every pair of element. So the given poset least upper bound as well as greatest lower bound exists for every pair of element. Elements. Therefore, it is a lattice. So basically, if it is a lattice, then it will be joint semi-lattice as well as a meet semi-lattice. If it is a lattice, then it will be a joint semi-lattice as well as a meet semi-lattice. Sir, what about this? Sir, again, least upper bound and greatest lower bound exists for every pair of element because D6. So anyway, so can I generalize? This that if I have a set Dn, then in set Dn we'll have the least upper bound for every pair of element as well as the greatest lower bound for every pair of element. So the set of all divisors of n with respect to divide will always be a lattice. Will always be a lattice. You don't need to think too much about that particular set, because in set of all the divisors of n for every pair of element, the least upper bound will exist and the greatest lower bound will exist. Therefore, it will always be a lattice with that particular poset will always be a lattice. So that's also a lattice. The lattice. What about this? Sir, it is a totally ordered set. It is a totally ordered set. Why? Sir, the linear chain. What did we say? That if the poset diagram for a poset looks like a linear chain, the poset diagram for a poset looks like a linear chain, then it will be a toe set. Then it will be a toe set, and every toe set, please remember, every toe set will be a lattice. Why? If you take any two elements, on this line, then the element on the upper side will be the least upper bound of that pair of element, and the element at the lower side will be the greatest lower bound of that that particular pair of elements. So a totally ordered set will always be a lattice. A totally ordered set will always be a lattice. Clear? Okay. So just note down certain points. We have understood the help of example also. Note down. If En is the set of all positive divisors of n. N is the obviously n is a positive integer. So if Dn is the set of all positive divisors of n, then poset. So it's obviously a poset set of any set of positive integer. This will be a set of positive integer with respect to divide is a poset. Then poset Dn with respect to divide is a lattice. Is always a lattice, I would say. Another statement that I can say is, I just do the intuition that if you have a totally ordered set, then if you take any pair of element, the element at the upper side in the Hasse diagram will be the least upper bound, the element at the lower side in the Hasse diagram will be the greatest lower bound. That means the least upper bound as well as greatest lower bound will exist for every pair of element in a toe set. So it will also be a load. So every toe set is always a lattice, not vice versa. A lattice need not be so set. You have seen an example. So this is a lattice, but it is not a totally ordered set. So if it is a totally ordered set, it is guaranteed that it will also be a lattice. But every lattice need not be a totally ordered set. Example 2 and 3 are the examples in which they are representing, these posets are actually corresponding to lattice, but they are not the totally ordered set. Now, if you have two or more maximals, it will not be a joint semi-lattice. Two or more minimals, it will not be a meet semi-lattice. If least upper bound exists for every pair of element, it will be a joint semi-lattice. If greatest lower bound exists for every pair of element, it will be a meet semi-lattice. Next concept is, sir, how do we denote a lattice? How do we denote a lattice? A lattice is generally, so like we have denote a poset using this. So this is our poset. This same poset will eventually become a lattice if in this poset least upper bound as well as greatest lower bound exists for every pair of element. Now, how do we calculate least upper bound and greatest lower bound? Will eventually depend on the relation. We said that, sir, if it is a set of real numbers and the relation is less than equals to, then the least upper bound and greatest lower bound will be defined by minimum and maximum. Right? Now, if it is a set of positive integers and the relation is divide, then the least upper bound will be defined by LCM, or generally not exactly, but may be defined by LCM, and the greatest lower bound will be defined by GCD if they are present in the set. Okay, sir, if I take A as a collection of set, of sets, and let's assume that relation is actually nothing but subset or equal. So what will be the least upper bound with respect to subset or equals to? So the least upper bound with respect to subset or equals to will be union, right? So if I take two subsets x comma y belonging to set A, then the least upper bound of x and y will be nothing but x union y, and the greatest lower bound of x and y will be x intersection y, something like that, if both x union y and x intersection y are present in the set. Apart from that, you will have to look at the set. X union y and x intersection y are not present, then you will have to look for other sets in the collection of set which are satisfying the property of least upper bound and greatest lower bound. Anyway, chalo. So let's come back to the same concept, that is, how do we denote a lattice? This is basically your lattice. Now in this, L is your set, and these two are the symbols which are representing the binary operation least upper bound and greatest lower bound. Don't worry about them. They are just for the notation purpose. They are just for the notation purpose, that in a lattice, obviously we know that least upper bound and greatest lower bound will exist for every pair of element. Now, somebody tells me that there are two elements A and B belongs to set L. Then how do we denote the least upper bound of A and B? So we denote least upper bound of A and B using this. How do we denote the greatest lower bound of A and B? So we denote the greatest lower bound of A and B using this. So this is just for the notation purpose. So you don't need to worry about that. So what is being represented by this or and symbol? They look like or and symbol in the propositional logic. So don't worry about them. They are just for the notation purpose, that how do we recognize something. So this is how we denote set, and these two are the binary operations corresponding to least upper bound and greatest lower bound. This will represent upper bound, will represent greatest lower bound. Clear? So anyway, so let's go back to the post. So what did we say? In a lattice, in a lattice, if somebody asks me that what is the least upper bound of 2 and 3, so if I write like this, then it will represent the least upper bound of 2 and 3 in this lattice. So is it a lattice? Yes. First of all, this terminology should be used in, with respect to lattice, because if it is not a lattice, then it is not necessary that least upper bound and greatest lower bound will exist for every pair of elements. So what is the least upper bound of 2 and 3? It will be denoted using this, and least upper bound of 2 and 3 will be 6. So what is the greatest lower bound of 2 and 3? The greatest lower bound of 2 and 3 is where they meet each other at the lower side. So they meet each other at 1. Therefore, the greatest lower bound will be 1. That we have already seen. Don't worry about that. Yeah. Now, sir, if this is the case, then the greatest lower bound of who's this? The greatest lower bound of 2 and 3 does not exist. Use the same notation. It need not exist. But in a lattice, least upper bound as well as greatest lower bound will exist for every pair of element. For it does not exist, therefore it is not a lattice. Okay, sir. Let's go back and try to some other things. So it's okay that this is how we denote the least upper bound and greatest lower bound. So there are certain properties. There are certain properties which are followed by the elements of the lattice. So what are they? So following properties holds true in our lattice. You take any lattice, any lattice, any lattice. If you take any lattice, then following properties holds true. What are they? First one is commutative. What does it mean? That if there are two elements A and B, then the least upper bound of A and B will be exactly same as the least upper bound of B and A. Similarly, the greatest lower bound of A and B will be exactly same as the greatest lower bound of B and A for all elements A and B belonging to lattice L. For all pair of elements A and B belonging to lattice L, apart from associative property. Associative property also we know. If we have three elements A, B and C, then either we take the least upper bound of A and B, and then we take the least upper bound of A and B with element C, then it will be exactly same as the least upper bound of B and C, then the least upper bound with A. Similarly, for the greatest lower bound, A, greatest lower bound with B, and then the greatest lower bound with C will be same as the greatest lower bound of A with the greatest lower bound of B and C for all ABC, for all triples belonging to L. So commutative property will always hold true in a lattice. Associative property will always hold true in any lattice for any triple of element. Idempotent law, what does it say? It says that if you take the least upper bound of A with A, it will be A. If you take the greatest lower bound of A with A, it will be A for all A belonging to lattice. Apart from that, absorption law. So it's absorption law. So it is exactly same as your absorption law of the digital or set theory. What does it say? So A, least upper bound with the greatest lower bound of A and B will be what? So if you try to understand this, then please try to visualize in terms of totally ordered set. Let's assume that this is your A, this is your B. Okay. Now if I take the least upper bound of A with the least upper bound of A and B. So if B is at the lower side of A, the greatest lower bound of A with B will be B. If this B is at the upper side, if B is at the upper side of A, then the greatest lower bound of A and B will be A, and in that case A least upper bound with A will be A. Now if B is at the lower side, then the least upper bound of A and B, sorry, the greatest lower bound of A and B will be B, and the least upper bound with A will come out as A, so it will be A. So ultimately it will absorb B. Similarly, the greatest lower bound of A with the least upper bound of A and B will be A for all A and B. So it's your absorption law from the digital logic or absorption law for the set theory, right? So it is exactly same. So this four properties will always hold true. Please make sure this four properties will always hold true in any lattice. But now your question may be that there are some other properties like distributive property. Does it also hold true in any lattice? No, sir. The distributive property may or may not hold true in a lattice. Yeah, note. Distributive property may or may not hold true in a lattice. Or not hold in a lattice. What does it mean? Sir, these four properties will always hold true. These four properties will always hold true. Along with that, if distributive property is also valid, then it will be called a distributive lattice. Then it will be called a distributive lattice. If there is any triple for which the distributive property does not hold true, then it will not be a distributive lattice. So we'll talk about. So it will eventually form a type of lattice. It will be a type of lattice. But anyway, I just told you a simple thing that if you take any lattice, then these four properties will always hold true. These four properties will always hold true. Some other properties which are there in your mind may or may not hold true. May or may not hold true. So anyway, we have seen, we have revised the concept of Hasse diagram. We have understood the concept of least upper bound and greatest lower bound of a pair of element in a poset. Today, we introduce the concept of a lattice, that is a poset in which least upper bound as well as greatest lower bound exists for every pair of element. Now, we try to understand the different types of lattice. We'll try to understand the different types of lattice. The very first thing is sublattice. The very first thing is sublattice. And I will give you the example of this sublattice in the tomorrow's class. I hope you know one thing, that this session is lattice and their types part 1. Tomorrow's session will be lattice and their types part 2. I cannot complete all the types of questions in a single session. Therefore, I have divided these into two parts. In today's class, I will give you the intuition regarding most of the things, but the concept of sublattice and some more practice questions will be discussed in the tomorrow's class. So it's the limitation of time. We cannot complete everything in a single class. So I hope you understand. But I will give you the definition of sublattice. But if you want, I can skip this definition as well. Or I can skip this definition. Yeah, we can safely skip this definition because it will not look. Yeah, we can skip this definition. So I'll give you the definition of sublattice also in the tomorrow's class. That will also be a type of lattice. That's perfectly fine. Don't worry about it. So just remember that there is a specific type which is called sublattice. There is a specific type which is called sublattice. Very good evening, Hemant. So we'll discuss it. Don't worry. But I know that if I just try to write down the definition and I do not give you an example, it will be very difficult for you to understand. Therefore, keep it for the tomorrow's class. We'll understand. We'll try to understand this. Another one is a bounded lattice. Bounded lattice. So let's come back to the definition. Lattice and try to understand that when exactly a lattice will be called a bounded lattice. So this is very simple actually. The definition may look clumsy. The definition may look clumsy, but the concept of a bounded lattice is very simple. So, I should first give you the intuition so that it will be easier for you to understand that a lattice maximum element or in a poset maximum element. Do you remember the maximum element? Go back. Sir, the element which is on the upper side of all the elements of the element with this. The element which is on the upper side of all elements of the poset will be called the maximum. 6. So 1 divide 6, so 6 is on the upper side of 1. 2 divide 6, 6 is on the upper side of 2. 3 divide 6, so 6 is on the upper side of 6. 6 divide 6, so 6 is on the upper side of 6. So 6 is on the upper side of all the elements. Therefore, 6 is the maximum element. It is also maximal. It is also maximal because there is no other element apart from 6 itself which is on the upper side of 6. Therefore, it is also maximal, but 6 is on the upper side of every other element of the poset. Therefore, it is a maximum element. So, is it necessary in a poset for the maximum element to exist? No. I'll give you an example, but anyway, sir, this is the maximum element. The element which is on the lower side of all other elements will be called minimum element, right? So, maximum element will be called upper bound of the lattice or universal upper bound. Minimum element will be called lower bound of the lattice or universal lower bound. Don't worry, all concept, but just a tricky definition. The lattice maximum element, if exist, is not necessary for maximum element to exist. In a lattice, maximum element, if exist, is called universal upper bound of the lattice and similarly minimum element, again, it need not exist. Minimum element, if exist, is called universal lower bound of the lattice. We are not lower bound of lattice. Okay, sir. So they need not exist. I'll give you an example in a while, but let me give you the proper definition of the bounded lattice. What is the definition? Hold on. Let L with respect to upper bound and lattice lower bound denoted by this symbol be a lattice. First, if there exists an element if there exists an element I, some element, some element I, if there exists an element I belonging to L such that in your set, such that if you take the least upper bound of I with any element A of the lattice L and it comes out as I. So if there exists an element I belonging to set L such that the least upper bound of A and I is equals to I for all A belonging to lattice L, then I is called upper bound of lattice L or universal upper bound. Upper bound of lattice L or universal upper bound. Okay. Next, second, if there exists an element O there exists an element O belonging to set L. In the same lattice L, if there exists an element O such that this I, which is becoming the upper bound, is with respect to least upper bound, such that the greatest lower bound of O with any element A comes out as O only for all elements of lattice L. So, if there exists an element O in the lattice L such that the greatest lower bound of any element of the poset with that element O comes out as O itself, then what do we call? Then O is called universal lower bound. Then O is called universal lower bound or lower bound of lattice L. So I hope you understand what will become the universal lower bound. The universal lower bound will be nothing but the minimum element of the poset. Universal upper bound will be nothing but the maximum of the poset. We already know how to check for the minimum element and maximum element in a poset. But it may not be, I mean, it may be possible in some posets that it's no minimum element or no maximum element. I'll give you an example. But first of all, in our lattice, if both I and O are present, a poset, if both I and O are present, then that particular lattice is called a bounded lattice. So, in a lattice in which both universal upper bound I and universal lower bound O, so universal upper bound and universal upper bound exist. A lattice in which universal upper bound and universal lower bound exist is called a bounded lattice. It's called a bounded lattice. Clear? So let's go back to the previous examples. Now you know, sir, the posets which are not lattice, there is no point of discussing that whether it is a bounded lattice or not. It is not a lattice. So what's the point of becoming a bounded lattice? Sir, it's not a lattice. It is not a lattice. So what about this? Sir, it is a lattice. And the maximum element is 12, minimum element is 1. So 12 is the universal upper bound. And this 1 is the universal lower bound. So same concept. Sir, the maximum element is the universal upper bound, minimum element is the universal lower bound. Another example, sir, this maximum 6 is the maximum element, therefore this is the universal upper bound of the lattice. You can actually check. If you take the least upper bound of any element with 6, it will be 6 itself. If you take the greatest lower bound of any element with 1, it will be 1 itself. Clear? Similarly, if you take any element, if you take the least upper bound of any element of this poset with 12, it will be 12. If you take the greatest lower bound of any element of this poset with 1, it will be 1. Therefore, it is universal lower bound and 12 is the universal upper bound. Similarly, in a totally ordered set, now this is your maximum element, so it is the universal upper bound. If you take the least upper bound of any element of this poset with 6, it will be 6 because it is at the top. If you take the greatest lower bound of any element with -1, it will be -1 because -1 is at the bottommost element. Clear? Makes sense? So you may say that, sir, in every lattice there will be a minimum element and maximum element. In every lattice there will be a minimum element and maximum element. So it's not necessary. Not necessary that all the lattice are bounded lattice. Just note down. Note. Uh, Not all the lattice are bounded. There may be some lattice are not bounded. So if I give an example, see if I say the set of natural number with respect to less than equals to is a lattice. Come on, is it a lattice? Take any two element. Take any two element from the set of this natural number. Take any two element from the set of natural number. Do you have the least upper bound and greatest lower bound for that pair of element in the set of natural number itself? Yes, sir. If you take any two natural number, the larger one will become the least upper bound and the smaller one will become the greatest lower bound. So for any two element, the least upper bound as well as greatest lower bound exist in this poset. Therefore, it is a lattice. But is it a bounded lattice? Is it a bounded lattice? Sir, in the set of natural number, do we know the largest natural number? Do we know the largest natural number? That is, do we know the value of I with which if you take the least upper bound of any element, then it will be I itself? No, sir. That will eventually be the largest natural number, but the largest natural number is not known. You may say infinite, but infinite not is not the largest number. Infinite plus one, infinite plus one will also be infinite, which is larger than the previous infinite. So that's the idea. We don't know the largest natural number. So we can say this is a lattice, but upper bound does not exist. Upper bound of this lattice does not exist. Upper bound of this lattice does not exist. Okay. Now, so what will be the lower bound? Sir, the smallest natural number will be 1. Therefore, the lower bound will be 1. If you take the greatest lower bound of any element with 1, it will come out as 1. Therefore, 1 is the universal lower bound or lower bound of the lattice. But we don't know the universal upper bound. Yeah. Similarly, sir, you may say that, sir, that means one will exist and another will not exist. No, it is not the case. Let's look at this example. If I take the set of all integers, positive as well as negative, if I take the set of all integers with respect to less than equals to, then it is a lattice. If you take any pair of integers, one will be smaller, another will be larger. Therefore, the least upper bound and greatest lower bound will exist. But do we know the largest integer? Do we know the smallest integer? No, sir. So, is the lattice, but not bounded. But not bounded. Universal upper bound and universal upper bound as well as universal lower bound does not exist. Okay. Now, the another thing that may come in the mind is so that whenever the sets are of infinite size, it will always be unbounded. No. So, another, please, if lattice is unbounded, if lattice is unbounded, then underlying set will be an infinite set. An infinite set. But converse of the statement need not be true. But converse of the statement need not be true. What does it mean? It means that it is not necessary for an infinite set to be unbounded. What? So can you please give us an example? Let's take example. If I define the set A as set of all real numbers x such that x is greater than 0 and less than equals to 0, less than equals to 1, and x is real number. So please tell me, how many real numbers are there between 0 and 1? How many real numbers are there between 0 and 1? Sir, it is an infinite set. Yes or no? So it is an infinite set because there are infinite real numbers between 0 and 1. Because there are infinite real numbers between and 1 is an infinite set. But A with respect to less than equals to a bounded lattice. Yes or no? Sir, if you take any two real numbers between 0 and 1, one will be largest, another will be smaller. That is, least upper bound and greatest lower bound will exist. And if you take any real number between 0 and 1, and if you take the least upper bound with 1 with respect to less than equals to, it will be 1. If you take any real number between 0 and 1, and if you take the greatest lower bound with 0 with respect to less than equals to, it will be 0. That is, for any pair of element or for any element of this set A, if you take the greatest lower bound with 0, it will be 0. If you take the least upper bound with 1, it will be 1. Therefore, the universal lower bound will be 0, universal upper bound will be 1. So it's a bounded lattice. Is a bounded lattice where I will be equals to 1 and O will be equals to 0. Right? So we know the universal upper bound and universal lower bound in this particular case. So one thing is guaranteed, that if it is unbounded, then for a finite set, it is not possible. For a finite set, it is not possible that in a lattice the least upper bound, the upper bound and lower bound of the lattice does not exist. But if it is unbounded, it is guaranteed that that set will be an infinite set. But not all the infinite sets will create an unbounded lattice. With the infinite sets also, it is possible to have bounded lattice. Yeah, so that's fine. So generally, the context is, that's a simple definition which you need to understand is, so the maximum element will be the upper bound, minimum element will be the lower bound. To talk about this particular example, sir, do we have any maximum element? No, sir. So we don't have the maximum element. That is, there is no element which is on the upper side of every element. Therefore, the universal upper bound does not exist. There is no minimum element as well as maximum element with respect to set of integers. Simple concept. The different ways of asking, but the concept is very simple. Now, once you have understood the concept of bounded lattice, let me introduce the concept of complement of an element of a lattice. Given a lattice, if somebody asks you that what will be the complement of a given element of the lattice, so the idea is complement can be defined, complement of an element can be defined only in a bounded lattice. First thing, complement of an element can exist only if lattice is a bounded lattice. The lattice is not bounded, complement will not exist for any element. Now, assume. So how do we define? So let L respect to upper bound and bound a bounded lattice where I, O, R where I and O are universal upper bound and lower bound of the lattice. I and or are the bounds of the lattice L. Right. Again and again, that universal upper bound and universal lower bound. Now, next, for an element, for an mm, for an element A belonging to that L. Now, we have a bounded lattice and we have this upper bound and lower bound of the lattice. So, for an element A belonging to set L, if there exists any element B belonging to set L, there exists any element B belonging to set L such that the least upper bound of A and B is actually equals to universal upper bound and lattice lower bound of A and B is equals to universal lower bound of lattice L. If there exists, if for element A there exists any element B, then A and B are called complement of each other. Then A and B are called complement of each other. Simple. So, in a bounded lattice for an element A, all such elements B such that the least upper bound of A and B equals to I and the greatest lower bound of A and B equals to O will be complement of each other. So, I'll give you an example, but before that, I just need to important points. What I and O are always complement of each other. I and O are always complement of each. That's fixed. Always complement of each other. It is guaranteed that the complement of I will be O and complement of O will be I. That is, the complement of universal lower bound will be universal upper bound and complement of universal upper bound will be universal lower bound. There will be no other complement for them. There will be no other complement for them. Now, please try to understand. In a bounded lattice, complement of an element need not exist. Now, when I say that, yeah, it's a bounded lattice, so does it mean that complement of every element will exist? No, it is not necessary. So, in a bounded lattice, complement of an element need not exist. So, it's not necessary for complement to exist for every element. Need not exist. And if exist, even if it exists, then it need not be unique. What does it mean? That means that complement need not exist for every element. And if exists, it is not necessary that every element will have a unique complement. There may be more than one complement for some element, and there may be no complement for some element. Okay? So if you want, you can write down. So there may be 0 or more complement to or more complements of an element. Okay. Now, that means the tricky thing. But anyway, we can define some other things based on the number of complement. Now, the next thing is complemented lattice. When do we say that the lattice is a complemented lattice? When do we say that the lattice is a complemented lattice? So the idea is quite simple, that if complement exists for every element of the lattice, then the lattice is called complemented lattice. We are only saying that the complement exists for every element. We are not saying that it should be unique, right? So if complement exists for every element of the lattice, if complement exists for every element of the lattice, then it is called a complemented lattice. Come on. Sir, we only said that complement exists for every element, but it need not be unique. Now, complemented lattice complemented lattice, every element will have at least one complement. At least one complement. What does it mean? At least one. That is one or more. That is one or. It's a complemented lattice. Now, let me give you an example. Let's say if this is your poset, or let's say this is your lower bound O, I, A, B. Please tell me what is the complement of O. So we already know complement of O will be I. We already know complement of I will be O. Now apart from that, let's look at the idea. So what will be complement of A? What will be complement of A? Sir, if we take the least upper bound of A and B, it will be I. If we take the least upper bound of A and B, it will be O. So the A and B are complement of each other. A and B are complement of each other. So fine. So you may say that there will be unique complement. No, it's not necessary. Come on. Let's take another poset. Let's take another poset. Assume that this is your poset, this is your I, your O. Come on. One thing is guaranteed, that complement of O will be I, complement of I will be O, and they will have unique complement. They will have unique complement. But now my question is, so what are the complements of A? What are the complements of A? Come on. One simple thing is that in a poset, the complement of an element cannot exist on the same line. What does it mean? I'll give you that intuition in terms of total ordered set, but please try to understand. If you take any two elements on this set, apart from universal lower bound and universal upper bound, then on the same set the complement cannot exist, or on the same line the complement cannot exist. Now, the complement of A cannot be I or O because their complements are unique. So, the least upper bound of A and B is I, the greatest lower bound of A and B is O, therefore B is the complement. Similarly, the least upper bound of A and C is I, the greatest lower bound of A and C is O, therefore C is also the complement of A. Similarly, if we look at the complement of B, what are the complements of B? Sir, A will be complement of B as well as C will be complement of. Similarly, look at the complement of C, then what are the complements of C? The complements of C. So C and A, least upper bound I, greatest lower bound O. So A is the complement. So C and B, least upper bound I, greatest lower bound O. So C and B are also complement. So now you know that this is also a complemented lattice. So this is a complemented lattice, this is also a complemented lattice. What else? O, I, A, B, C. Fine, sir. The complement of O will be I. Complement of I will be O. Okay. So, what is complement of A? Sir, the least upper bound of A and B is I. The greatest lower bound of A and B is O. Therefore, B is one complement. The least upper bound. Sir, where do they join each other at the upper side? Sir, at I. Where do they meet each other at the lower side? Sir, at O. So, the least upper bound of A and C is I. The greatest lower bound of A and C is O. Therefore, C is also the complement of A. Now, sir, what will be complement of B? Sir. Complement of B. Please. Sir, complement of B cannot exist on this line. Then if possible, then the complement of B can be A. No other element can be complement of B. So let's look at, let's check with A. So least upper bound of A and B is I, and then the greatest lower bound of A and B is O. Therefore, the complement of B will be A. No other element can be complement of B. Similarly, complement of C is also A. No other element can be complement of C. So these are all the complemented lattice. These are all the complemented lattice. It may be possible that every element has exactly one complement. It may be possible that some element has more than one complement, but every element will have at least one complement. Okay. Now let's go back to the definition of a complemented complement. Go back to the definition for complement of a lattice, and if complement exists for every element, then it will be called a complemented lattice. But what did we say? Sir, in a normal bounded lattice, there may be zero or more complement of an element. So let's try to understand that in our POSET, what happens. This is the, let's assume that this is your O, this is your I, and these are the elements A, B, C. And that's another element. Let's call it X. Now, one thing is guaranteed, that the complement of O will be equals to I, and complement of I will be equals to. Now, if I ask you that what will be complement of X, so please try to understand. On a line, if you take any element above X, then the greatest lower bound of that element with X will be equals to X. It cannot be O. If you take any element on the line apart from universal lower bound and universal upper bound, then that for that particular element, the complement of X cannot exist above X. Why? Because if you take any element above X and if you try to calculate the greatest lower bound of that element with X, it will be X. It can never be O. But what's the definition? That two elements can be complement of each other only if the greatest lower bound of those two elements is equals to O. If you take any element above X, then the greatest lower bound of that element with X will be X itself. It can never be O. Similarly, if you take any element below X, then the least upper bound of that element with X will be equals to X. It cannot be I. So, above X, no element can justify the condition of greatest lower bound equals to universal lower bound. Therefore, the complement of X cannot exist above X. Similarly, the complement of X cannot exist below X, because that will not justify the condition with respect to universal upper bound. So that's the idea, that on a line, the complement of universal lower bound will be equals to universal upper bound. Universal upper bound will be equals to universal lower bound, and complement of any other element cannot exist on the same line. Does not exist. So please remember, in our totally ordered set, complement of O will be I, complement of I will be O, and complement does not exist for any other element. In our totally ordered set. a totally ordered set. I complement equals to O complement equals to I, and complement does not exist for any other element. Not exist for any other element of totally ordered set. Okay, so that's fine that there may be no complement for some elements. There may be no complement for some elements. There may be more than one complement for some elements in our lattice, but please try to understand, if we look at this totally ordered set, is it a complemented lattice? No, sir. The complement does not exist for A, B, X, C, D. So there are many elements for which complement does not exist. Therefore, it is not a complemented lattice. So the moment I say X complement does not exist, therefore not a complemented lattice. Not a complemented lattice. Okay, let me, because I have used logic, not a complemented lattice. All are complemented lattice. Every element has at least one complement. Every element has at least one complement. Every element has at least one complement. So can I say all are complemented lattice? All examples are of complemented lattice. Okay, that's it. So up to this, everything is okay. The next types of lattices, that what do you mean by distributive lattice? What do I mean by Boolean lattice? And what do I mean by sublattice? These three different types of lattices will be covered in the next class. Then we have understood the concept of lattice, joint semi-lattice, meet semi-lattice. How do we denote the least upper bound and greatest lower bound in a lattice? What are the properties which are satisfied by the elements of a lattice with respect to least upper bound and greatest lower bound? Distributive property may or may not satisfy, so that will define the distributive lattice. But for time being, leave it, because there are some other things those are important with respect to distributive lattice. So apart from that, we have understood the concept of bounded lattice. That what do I mean by a bounded lattice? A lattice which both maximum and minimum element exists will be called bounded lattice. The complement of an element of a lattice will be defined only the lattice is a bounded lattice. If lattice is unbounded lattice, then complement will not exist for any, because for complement to exist, we must have I and O defined in that lattice. If I and O themselves are not defined, then we cannot define the complement for any element of the lattice. So these are certain things. Once we understand that number of complements for an element of a lattice may be 0 or more, then we define the concept of a complemented lattice, that a lattice in which every element has at least one complement will be called complemented lattice. So there may be some lattice in which every element has at least one complement, but there may be some lattice in which some of the elements do not have any complement. So on the basis of that, we'll try to define some other types of lattices, that is distributive lattice. So this will be our distributive lattice. Then we'll try to define the Boolean lattice, and one more type of lattice will be sublattice. So we'll discuss these three types of lattice in the tomorrow's class, along with some questions based on the concept of sets and relations. So tomorrow's session will be the last session for sets and relation. Then we'll talk about functions and group theory, but that will be the last session for set theory point of view. That will be all for this particular session. Thank you very much. I hope you have understood the concept of joint semi-lattice, meet semi-lattice, and lattice. You have understood the concept of bounded lattice. You have understood the concept of complement of an element lattice, you have understood the of complementary lattice. If I just give you a basic concept related to distributive lattice, then okay, then I can only say one thing, that every element has at most one complement. At most one complement. So why are not complete topic? So that I will be able to quickly revise this three concept, and based on that I'll be able to give you the definition of distributive lattice and we'll move ahead. So that will be all for this particular session. Please go through all these slides once again so that you will understand the basic difference between a POSET and a lattice, and you will be able to understand the different types of lattices as well. But it will not be complete, so you guys can leave it for one day and can try to revise today's session as well as tomorrow's session in a single go, so that you will be comfortable with all the concept of the lattices along with the different types of lattice. That will be all. Thank you very much for joining this session. Have a great time. Keep learning. Thank you.